Every year, the world produces around 4 billion tons of cement, enough to build more than 400 Three Gorges Dams. But that massive scale comes at a cost. Cement production is responsible for up to 8% of global CO2 emissions, roughly 3 times as much as the entire aviation industry, and surprisingly, the source of all those emissions is something incredibly ordinary: the cheap gray powder found on construction sites everywhere. So how do simple materials like limestone and clay become cement? And why does making it have such a huge impact on the climate? To find out, we're going to follow limestone from the moment it is blasted out of the quarry, through the massive machines and extreme temperatures of a cement plant, until it finally becomes one of the most widely used construction materials in the world. Before we follow that piece of limestone on its journey, there is one thing we need to clear up. Many people still confuse two materials that may seem almost identical: cement and concrete. But they are actually completely different. Concrete is a mixture of cement, sand, gravel, and water. Cement is simply the binding material that holds everything together and allows the mixture to harden into a solid mass. This seemingly simple binder plays a crucial role in creating concrete, the most widely used man-made material on Earth. The main ingredients used to make cement are surprisingly simple: limestone, which makes up around 80% of the raw material, and clay. But turning these ordinary materials into a powder capable of helping build everything from houses to massive dams requires a series of extreme transformations, including some of the highest temperatures found anywhere in the materials industry. At Rogers City, Michigan, home to one of the largest limestone quarries in the world, the process begins with an explosion that tears through the rock face. Limestone, which makes up around 80% of the raw materials used to produce cement, is blasted loose by the thousands of tons in just seconds. It is then crushed at the quarry into pieces roughly the size of a fist before traveling by conveyor belt to the cement plant. There, the limestone is mixed with clay and small amounts of other materials, such as iron ore and silica sand, before being ground into a fine powder known as raw meal. At this stage, even a small change in chemical composition can affect an entire batch of clinker. One of the most important measurements is the lime saturation factor, which indicates whether the amount of calcium is properly balanced with the silica, aluminum, and iron in the mixture. The composition is continuously monitored using X-ray analysis to keep the raw meal as close as possible to its target chemistry. If there is more lime than the other components can combine with, free CaO can remain in the clinker, potentially causing expansion and making the finished cement unstable. Once the raw meal reaches the correct composition, it is blended and homogenized inside massive silos, ready to enter the most extreme stage of the entire process. This is where limestone pays the highest price for becoming cement. The raw meal leaves the silo and enters the preheater tower, a massive steel structure that rises dozens of meters into the air and contains multiple stages of cyclones. The powder moves downward while hot gases from the kiln rise in the opposite direction, rapidly heating the raw meal from around 100 Clyders to more than 800 hybrid Ts. At the base of the tower is the precalciner, where calcium carbonate in the limestone breaks down into calcium oxide and CO2. This CO2 comes directly from the raw material itself, not just from the fuel burned to heat the kiln. Around 90% of this reaction is already complete before the material even enters the kiln. The rotary kiln is the heart of the cement plant. It is a massive steel cylinder, typically around 60 to 100 meters long, slightly tilted and constantly rotating. Some kilns can operate continuously, for an entire year before requiring major maintenance. Inside, the material is heated to around 1450 degrees, while the flame from the burner can exceed 2030 degrees. At these extreme temperatures, calcium oxide reacts with silica, alumina, and iron oxide to form new minerals that give cement its binding properties. This process is known as sintering. The result is clinker, hard, rounded nodules measuring roughly 3 to 25 millimeters across. They leave the kiln at temperatures above 1,200 degrees, glowing bright orange-red as if they had just been pulled from a stream of molten lava. But clinker is still a long way from the familiar bag of cement. What happens next is the complete opposite. Instead of being heated, it now needs to be cooled as quickly as possible. The moment clinker leaves the kiln, the hotter it is, the faster it needs to cool. Powerful streams of air are forced through the clinker as it moves across a great cooler, dropping its temperature from more than 220 Q to around 100 degrees in just a few minutes. But that heat is not wasted. After absorbing heat from the clinker, the hot air is sent back into the kiln system and reused for combustion. In a way, the clinker helps provide the heat for the next batch, using energy left over from its own production. Once cooled, the clinker is ground together with around 3 to 5% gypsum. Without gypsum, cement could begin setting almost immediately after coming into contact with water. Gypsum provides valuable extra time for concrete to be mixed, poured, and shaped before it begins to set. After grinding, each batch of cement is tested for fineness, setting time and strength before being transferred into storage silos, ready to be shipped in bulk or packed into bags. At this point, the cement is finally complete. But one question still remains. Why does producing this seemingly simple gray powder generate nearly 8% of the world's CO2 emissions? The answer lies in the precalciner we saw earlier. When heated, the calcium carbonate in limestone breaks down into calcium oxide and CO2, an unavoidable chemical reaction. Around 60 to 65% of the CO2 released during clinker production comes directly from this reaction, while most of the rest comes from the fuel burned to generate the intense heat required by the process. On average, producing 1 ton of cement generates around 0.6 tons of CO2. That figure has fallen by more than 20% since 1990, partly because manufacturers have gradually reduced the amount of clinker used in cement. But those improvements have still not been enough to offset the continued growth in global production. This is what makes cement one of the toughest challenges in the race to cut carbon emissions. Many industries can dramatically reduce their emissions by switching to cleaner energy. With cement, that only solves part of the problem. Most of its emissions come from the chemical reaction that turns limestone into lime, a reaction that remains necessary even if the entire plant runs on clean energy. That is why cement, along with steel and heavy chemicals, is considered one of the hardest industries in the world to decarbonize. So if we cannot completely eliminate the reaction that creates this CO2, the question is no longer how to stop it from being produced, but what we can do with it once it is. While many modern concrete structures begin to crack and deteriorate after just a few decades, the Pantheon in Rome, with its massive, unreinforced concrete dome, has remained standing for nearly 1,100 years. Part of the secret lies in a binding material very different from modern Portland cement. The Romans combined lime with pozzolana, a mineral-rich volcanic ash. In 2023, researchers at MIT uncovered another surprising detail. Ancient Roman concrete contains small pieces of lime known as lime clasts. When water enters a crack and reaches these clasts, calcium-rich material can dissolve and then recrystallize as calcium carbonate, gradually sealing the crack before it spreads. This gives the material a natural self-healing ability that ordinary Portland cement concrete does not possess to the same extent. In some ancient Roman harbor structures, seawater did not simply fail to destroy the concrete. Instead, it actually encouraged the formation of new minerals within the material, contributing to its remarkable long-term durability. 2,000 years later, these discoveries are leading scientists back to a question that once seemed settled. Does the cement of the future really have to be made the way we make it today? That question is not just philosophical. It is becoming increasingly urgent because the cement industry is simply too large for any single solution to transform it. The world still produces around 4 billion tons of cement every year. China alone accounts for nearly half of global production, while Vietnam is on track to overtake the United States and move into the world's top 3 producers. At this scale, solving cement's CO2 problem will require changes across the entire production process, not just one breakthrough technology. One solution has already moved from theory into the real world. In 2025, Heidelberg Materials launched the world's first cement plant with an industrial-scale carbon capture system in Brevik, Norway. It is designed to capture around 400,000 tons of CO2 each year. That is still only a tiny fraction of the industry's enormous global emissions, but it proves that capturing the CO2 that is difficult to avoid is no longer just an idea on a drawing board. At the same time, many manufacturers are reducing the amount of clinker used in cement. Part of it can be replaced with fly ash and blast furnace slag, which are byproducts of other industries, or with calcined clay, which can be produced with lower emissions than traditional clinker. After nearly 2 centuries of relying on the Portland cement formula, these changes may be the beginning of an industry, rewriting the very recipe that helped build the modern world. From an explosion deep inside a quarry to a bag of cement on a construction site, this seemingly ordinary gray powder goes through a far more extreme journey than its appearance would ever suggest. Cement is perhaps one of the most overlooked materials of modern civilization. No one takes a photo next to a bag of cement, yet almost every building we live in, work in, or walk past begins with it. The question is no longer whether we need cement, but whether it can continue building our world without continuing to heat the planet.